May 16, 1943, RAF Scampton, Lincolnshire, England. The briefing room fell silent as Wing Commander Guy Gibson pulled back the curtain covering the wall-mounted map. 133 aircrew members, the entire complement of 617 Squadron, stared at what had been hidden from them for 6 weeks of relentless training. 3 red lines stretched from their base across the North Sea, penetrating deep into Germany's industrial heartland. The targets were dams, the Möhne, the Eder, and the Sorpe. But it wasn't the targets that caused the collective intake of breath. It was the altitude notation marked along each route in Gibson's precise handwriting. 60 feet. Not 6,000 feet, not 600 feet. 60 feet above the water, lower than the trees along the shoreline. So low that a moment's inattention would send a Lancaster bomber weighing 30 tons and carrying a 9,000-pound experimental bomb straight into the surface at 240 miles per hour. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Flight Lieutenant Dave Shannon, pilot of Lancaster AJL, would later recall that moment with absolute clarity. When Gibson said 60 feet, I thought he'd made a mistake. Shannon wrote in his debriefing notes. Then I looked at his face and realized he was deadly serious. We'd be flying lower than German church steeples, below their radar, right into the heart of the Reich. The room went completely quiet. You could hear men breathing. The mathematics of survival were brutal. At 60 feet altitude, a Lancaster had perhaps 1.5 seconds between mechanical failure or pilot error and catastrophic impact. The Lancaster cruised at 240 miles per hour, which translated to 352 feet per second. At 60 feet above water, there was no room for recovery from a mistake. The pilots would maintain this suicidal altitude for over 400 miles across enemy territory, navigating by moonlight and dead reckoning, while German flak batteries and night fighters hunted them. Gibson stood at the front of the room, 24 years old, already a veteran of 173 combat missions. His face showed the strain of command, the knowledge that many of the young men watching him would not return from this mission. He had personally selected each of the 19 Lancaster crews in 617 Squadron, the best pilots in bomber command, the best navigators, the best bomb aimers, the best flight engineers. They would need every ounce of that skill. Gentlemen, Gibson began, his voice carrying the clipped precision of a Cambridge education and the weight of combat experience. You've been training for 6 weeks without knowing the target. Now you know why. This mission cannot be flown at normal bombing altitude. It cannot be flown by normal methods. The weapon we're carrying requires absolute precision. We must release at exactly 60 feet altitude, exactly 425 yards from the dam face, at exactly 240 miles per hour. Any deviation, and the weapon will not work. The weapon was Barnes-Wallace's bouncing bomb, a cylindrical device that would be spun backwards at 500 revolutions per minute, then released to skip across the water like a stone, strike the dam wall, sink, and detonate at a predetermined depth. The physics were elegant. The execution would be anything but. Flight Sergeant George Chalmers, wireless operator on Lancaster AJO, captured the mood in a letter he wrote to his mother that afternoon, before the mission briefing became classified. We finally know what we've been training for, he wrote. I can't tell you what or where, but I can tell you this. It's the sort of thing that will either go down in history or go down in flames. Probably both. The altitude we're flying at would make a barnstormer nervous. But if it works, if we pull this off, it could change the war. What Chalmers and the rest of 617 Squadron didn't fully understand yet was why flying at 60 feet was not just mission tactics, but survival necessity. The answer lay in a technology that had revolutionized air warfare and created an invisible web of detection across occupied Europe. A technology that could see bombers approaching from 100 miles away, vector fighters to intercept them, and alert flak batteries to their exact altitude and heading. A technology that had turned daylight bombing into a calculated bloodbath and made even night operations increasingly deadly. That technology was radar, and flying at 60 feet was the only way to stay invisible to it. The radar floor, that minimum altitude below which detection became impossible due to the curvature of the Earth and ground clutter interference, was approximately 200 to 300 feet, depending on terrain and radar type. By flying at 60 feet, Gibson's crews would slip beneath that floor, invisible to German early warning systems until they were directly over their targets. The briefing continued for 2 more hours. Navigation checkpoints, flak battery locations, fighter patrol patterns, wireless silence protocols, emergency procedures. The crews absorbed it all with the professional focus of men who knew their lives depended on remembering every detail. At 1800 hours, they were dismissed to their aircraft. At 21:39 hours, Gibson's Lancaster lifted off from Scampton's runway, followed at precisely timed intervals by the other 18 aircraft. They flew east toward the North Sea, descended to wave-top height, and vanished from British radar screens. In Germany, the radar operators saw nothing unusual. The night was quiet. The Rhine Valley lay peaceful under the moon. The dams stood unguarded except for their usual anti-aircraft positions. And then, without warning, 19 four-engine bombers appeared at rooftop height over the reservoirs, already beginning their attack runs. By the time the defenders understood what was happening, the first bombs were already striking the Möhne dam. The attack that would breach 2 major dams and flood the Ruhr Valley had achieved complete tactical surprise. The Germans never saw them coming. The technology that forced bombers to fly at suicidal altitudes began development 8 years before Gibson's crews attacked the dams. In 1935, British scientists working at the Radio Research Station in Slough discovered that radio waves could detect aircraft at significant distances. Robert Watson Watt, a Scottish physicist who had been studying atmospheric phenomena, realized that reflected radio energy could locate aircraft with precision impossible for human observers or sound detectors. By 1936, the British Air Ministry had begun constructing the Chain Home radar system, a network of transmitting and receiving stations along England's eastern and southern coasts. Each Chain Home station consisted of 360-foot tall steel towers, transmitting pulses of radio energy at frequencies between 20 and 30 megahertz. When these pulses struck aircraft, a tiny fraction of the energy reflected back to receiver stations equipped with 240-foot wooden towers supporting receiver antennas. The system was crude by later standards but revolutionary in capability. Chain Home radar could detect large aircraft formations at ranges exceeding 100 miles, and track them continuously as they approached. The system operated on wavelengths between 10 and 15 meters, which provided good range but limited precision. Altitude determination was particularly difficult. The system worked by comparing signal strength at receiver antennas mounted at different heights, a technique that became increasingly inaccurate above 15,000 feet. But the critical limitation was not at high altitude. It was at low altitude. The radar horizon, the maximum distance at which radar could detect an aircraft, was determined by the same physics that limited visual observation, the curvature of the Earth. Radio waves travel in straight lines. They cannot bend around the Earth's surface. An aircraft flying at 60 feet altitude, below the radar horizon, simply could not be detected until it came much closer to the radar station. The mathematics were straightforward. The radar horizon in miles equaled 1.23 times the square root of the radar antenna height in feet, plus 1.23 times the square root of the target aircraft altitude in feet. A Chain Home transmitter at 360 feet height could theoretically detect an aircraft at 30,000 feet altitude from approximately 250 miles away, given sufficient transmitted power and receiver sensitivity. But that same radar station could detect an aircraft at 60 feet altitude from only 33 miles away. This detection range reduction was compounded by ground clutter Radio waves reflecting from terrain features, buildings, trees, and water surfaces created a constant background of reflected energy that masked aircraft flying at very low altitude. The combination of radar horizon limitations and ground clutter interference created what operators called the radar floor, an altitude below which detection became unreliable or impossible. For chain-home radar, that floor was approximately 200 to 300 feet, depending on terrain. German radar technology developed along parallel lines with some significant differences. The Freya early warning radar, deployed extensively along the Atlantic Wall and throughout occupied Europe by 1942, operated at frequencies between 120 and 130 MHz, providing better precision than chain-home but somewhat shorter range. A Freya installation could detect large aircraft formations at approximately 75 miles range when operating optimally. The Würzburg precision tracking radar, used to direct both night fighters and flak batteries, operated at frequencies around 560 MHz with a large parabolic reflector approximately 10 feet in diameter. Würzburg could track individual aircraft with remarkable precision, determining range to within 300 feet and bearing to within 1/3 of 1 degree. These precision radars guided German fighters directly to bomber formations and provided flak batteries with exact targeting data. But all radar systems, British and German alike, suffered from the same fundamental limitation. They could not defeat the radar horizon or see through ground clutter at very low altitudes. An aircraft flying at or below 200 feet could remain undetected until it was nearly overhead. The tactical implications became clear during the daylight bombing campaigns of 1942 and early 1943. Bomber formations approaching at normal operational altitudes between 15,000 and 25,000 feet appeared on German radar screens when they were still 100 to 120 miles from their targets. This provided German fighter controllers with 20 to 30 minutes warning. Fighters could take off, climb to altitude, position themselves ahead of the bomber stream, and execute coordinated attacks. The bombers faced the entire journey to target under observation, with defenders tracking their every move. The statistics were devastating. During the first 5 months of 1943, RAF Bomber Command flew 21 major raids against German industrial targets. Average loss rate was 4.7% per mission. On some raids, losses exceeded 8%. At this rate, bomber crew members had virtually no chance of surviving the required 30-mission tour. The mathematics were simple and brutal. 8% losses per mission meant fewer than 5% of crews would complete 30 missions. American 8th Air Force experienced similar losses during unescorted daylight missions deep into Germany. The August 17th, 1943 raids on Schweinfurt and Regensburg, which occurred 3 months after Operation Chastise, would lose 60 bombers out of 376 dispatched, a 20% loss rate in a single day. Early radar detection was a primary factor in these losses. German controllers used radar tracking to position fighters optimally and vector them continuously to intercept bombers. The tactical problem seemed insoluble. Strategic bombing doctrine required hitting specific industrial targets deep inside Germany. Reaching those targets meant flying through radar-covered airspace where every mile of the approach was observed and reported. Fighters and flak batteries had 20 to 30 minutes advance warning to prepare their reception. Bomber formations might as well have been broadcasting their position, heading, altitude, and speed continuously, which, from the perspective of German radar operators, they essentially were. The solution, when it emerged, seemed insane. Fly below the radar floor, accept the collision risks, the flak vulnerability, the navigation difficulties, and the physical strain of maintaining precise formation at extreme low altitude. Trade the safety of height for the invisibility of staying below the radar horizon. It was a devil's bargain that would require extraordinary courage and skill to execute. But for certain high-value targets where surprise was essential, it was the only way to arrive undetected. The mathematical reality of radar evasion was both elegant and unforgiving. The Earth's curvature, which had limited human observation since the dawn of warfare, imposed the same fundamental constraint on radio waves. Understanding this limitation would provide bomber crews with a narrow corridor of invisibility, purchased at the price of flying lower than any sane pilot wanted to contemplate. The physics were straightforward, but the implications were profound. Radio waves propagate in straight lines through the atmosphere. They cannot bend around obstacles or follow the Earth's curvature. An aircraft flying below the geometric horizon relative to a radar transmitter exists in a shadow zone where radio waves simply cannot reach. The challenge was calculating precisely where that shadow began. Telling and preparing this story took us a lot of time. So, if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. British scientists at the Telecommunications Research Establishment at Malvern worked through the equations in late 1941. The radar horizon distance in nautical miles could be calculated as 1.06 times the square root of the transmitter antenna height in feet, plus 1.06 times the square root of the aircraft altitude in feet. For a typical German Freya radar installation with antennas mounted approximately 100 feet above surrounding terrain, detection range varied dramatically with aircraft altitude. A bomber at 20,000 feet altitude could be detected at 168 nautical miles. The same bomber at 5,000 feet dropped to 85 nautical miles detection range. At 1,000 feet, detection range fell to 45 nautical miles. At 300 feet, just 23 nautical miles. And at 100 feet altitude, the detection range collapsed to barely 14 nautical miles. But theoretical calculations meant nothing if pilots couldn't maintain precise altitude in combat conditions. The margin for error at 100 feet was measured in seconds. A Lancaster bomber at cruising speed of 240 miles per hour covered 352 feet every second. At 100 feet altitude, a distracted pilot had perhaps 1/3 of a second between the moment he started descending and the instant his aircraft struck the ground. The solution came from an unlikely source: submarine warfare. American engineers had developed radar altimeters for aircraft in 1938, using the same principles as echo sounders used by ships. A radio altimeter transmitted a continuous frequency-modulated radio signal downward and measured the frequency difference between transmitted and reflected signals. This frequency difference was directly proportional to altitude, and the instrument could measure height above terrain with accuracy of plus or minus 5 feet. The SCR 718 radio altimeter, which entered service with the RAF in 1942, revolutionized low-altitude flying. For the first time, pilots could maintain precise height above terrain in darkness or instrument conditions, without visual reference. The device was particularly valuable over water, where visual altitude estimation was notoriously unreliable. Many pilots had flown directly into water, believing they were still 50 or 100 feet above the surface. For Operation Chastise, Barnes-Wallis and the 617 Squadron engineering staff developed an even more precise system: spotlights. 2 spotlights were mounted in the Lancaster's nose and tail, angled downward so their beams converged at exactly 60 feet altitude. When the 2 pools of light on the water merged into a single figure-8 pattern, the aircraft was at precisely the correct height for bomb release. Flight Engineer Sergeant John Pulford would lie prone in the nose of Gibson's Lancaster, watching those pools of light and calling corrections. Down, down, steady. Up a bit, steady at 60 feet. The risks of low-altitude flight extended far beyond collision with terrain. German anti-aircraft defences were optimised for different altitude bands. Heavy flak, the 88mm guns that could reach 30,000 feet, were relatively ineffective against fast-moving targets below 1,000 feet. The traverse and elevation rates of heavy flak mounts couldn't track low-level aircraft moving at 300 miles per hour or more, but light flak was lethal at low altitude. 20mm and 37mm automatic cannons could fire 20 rounds per second with flat trajectories. A gunner who saw a bomber at low level had only to point and fire. No complex calculations of lead angle or time of flight. Just aim and shoot. The bomber would fly directly through the stream of shells. Small arms fire became a significant threat at extreme low altitude. A rifle bullet fired from a church tower or factory rooftop could penetrate a bomber's fuel tanks or kill crew members. During low-level attacks, Lancaster crews reported hearing the distinctive crack of rifle bullets striking their Resputers, aircraft fuselage, a sound they never experienced at normal bombing altitude. Obstacles presented constant danger. Power transmission lines, industrial chimneys, radio towers, and church steeples all posed collision hazards. In darkness or poor visibility, these obstacles became invisible until the last moment. Navigation at low level required absolute concentration. The navigator had to know precisely where every obstacle along the route was located and warn the pilot in time to climb over or maneuver around them. The physical demands on crews were extraordinary. Pilots maintained formation at low altitude by visual reference to other aircraft and terrain features, while simultaneously monitoring instruments, watching for obstacles, and listening to navigator calls. The mental workload approached the limits of human capability. After 2 hours of maximum intensity low-altitude flying, pilots were physically and mentally exhausted. Weather became a critical factor. Low cloud, fog, or rain reduced visibility to the point where low-altitude flying became impossible. A cloud base at 300 feet meant pilots couldn't fly below the radar floor without entering instrument conditions where collision with terrain was virtually certain. Mission planning had to account for weather along the entire route. A single area of low cloud or fog could force cancellation. Wing Commander Gibson described the sensation in his combat report filed after the dam's raid. Flying at 60 feet at night requires total concentration every second. You're watching the altimeter, watching the spots of light from the altitude lamps, watching for obstacles, maintaining position in formation, listening to the navigator, and trying to avoid being blinded by searchlights or confused by flak bursts. It's the most demanding flying I've ever done. One moment of inattention, and you're dead. Despite these risks, the radar shadow offered something invaluable: invisibility. A formation flying at 100 feet could penetrate 200 miles into German territory before appearing on radar screens, arriving over targets with perhaps 5 minutes warning instead of 30 minutes. For missions where surprise was essential, where the tactical advantage of appearing unannounced outweighed the risks of low-altitude flying, the radar flaw represented the difference between success and catastrophic failure. The question was whether bomber crews could be trained to operate in this narrow corridor between invisibility and death, and whether they would survive the learning process. The RAF's first serious experiments with low-altitude bombing came from desperation rather than tactical innovation. In 1941, German capital ships posed a direct threat to Atlantic convoys, and conventional high-altitude bombing had proven completely ineffective against moving warships. Bomber Command began testing low-level attacks with the grim understanding that crews would face murderous defensive fire, but might actually hit their targets. On December 18, 1941, Flying Officer Kenneth Campbell led a lone Bristol Beaufort torpedo bomber in a daylight attack on the German battleship Gneisenau in Brest Harbour. Campbell flew across the harbour at 50 feet altitude, threading between flak ships and shore batteries, dropped his torpedo at 200 yards range, and was shot down immediately afterward. The torpedo struck Gneisenau below the waterline, putting her out of action for 8 months. Campbell received a posthumous Victoria Cross. The mission proved that low-altitude attacks could achieve hits impossible from high altitude, but the price was almost certain death. The Channel Dash of February 12, 1942, demonstrated the limitations of hastily planned low-level attacks. German battleships Scharnhorst and Gneisenau, accompanied by the heavy cruiser Prinz Eugen, made a daylight dash up the English Channel from Brest to German ports. RAF Bomber Command scrambled every available aircraft to stop them. The attacks were uncoordinated chaos. Squadrons arrived piecemeal, attacked individually, and were slaughtered by layered defences. 242 Squadron flew 6 Fairey Swordfish torpedo bombers at wave-top height through a storm of anti-aircraft fire. All 6 aircraft were shot down. Not a single torpedo hit. Beaufort squadrons followed with similar results. By day's end, the RAF had lost 42 aircraft without inflicting significant damage. The German ships reached port safely. The disaster revealed that low-altitude attacks without careful planning, specialized training, and appropriate tactics were simply mass suicide. But Bomber Command learned from failure. Squadron leader John Nettleton absorbed those lessons and applied them to planning an attack on the MAN diesel engine factory in Augsburg, deep in southern Germany. The factory produced engines for German U-boats and panzers. Destroying it would impact both the submarine campaign and armoured warfare. But Augsburg lay 450 miles from England, far beyond fighter escort range. Any high-altitude attack would be detected hours in advance. Nettleton proposed a daylight, low-altitude strike using Lancaster bombers. 12 aircraft from 44 and 97 squadrons would fly across France at treetop height, arrive over Augsburg undetected, climb to 1,000 feet for their bombing run, then escape at low level. The crews trained for 3 weeks, practicing formation, flying at 100 feet altitude, navigation at extreme low level, and the climb-bomb dive sequence required for the actual attack. April 17, 1942. 12 Lancasters took off from RAF Waddington at 1500 hours, formed up over England, and descended to 200 feet as they crossed the Channel. The plan called for flying between known German radar stations, using valleys and terrain features to mask their approach. For 2 hours, the gamble worked. The formation penetrated deep into France undetected, flying so low that German soldiers on the ground watched them pass with stunned disbelief. Then, 90 miles short of Augsburg, the formation crossed directly over a German fighter airfield. Luftwaffe pilots scrambled immediately, pursuing the Lancasters without needing radar guidance. What followed was carnage. German Bf 109 fighters attacked from astern, where Lancaster defensive armament was weakest. 4 bombers were shot down during the long chase to Augsburg. The remaining 8 pressed on, climbing to bombing altitude over the target despite intense flak. The bombing was accurate. Several factory buildings were destroyed, but 3 more Lancasters were lost over the target or during the escape. 7 of the original 12 aircraft failed to return. Squadron leader Nettleton survived and received the Victoria Cross. The mission demonstrated that low-altitude penetration could achieve surprise, but losses were called unsustainable unless every element was executed perfectly. Analysis of the Augsburg raid identified critical lessons. First, low-altitude flight must be maintained throughout the mission. The climb to bombing altitude over Augsburg allowed flak batteries precious seconds to acquire targets. Second, routes must avoid German fighter bases. Once fighters had visual contact, radar became irrelevant. Third, timing was crucial. The afternoon attack meant long hours of return flight in daylight. Night provided additional protection. These lessons informed the development of specialized low-level tactics through late 1942. The Pathfinder Force, established in August 1942, developed precise low-altitude navigation techniques. Crews learned to use rivers, lakes, coastlines, and prominent terrain features as visual checkpoints. Maps were marked with power lines, radio towers, and other obstacles along planned routes. Training intensity increased dramatically. Pilots practiced low-altitude formation flying until they could maintain precise position at 100 feet in darkness with only moonlight for reference. Navigators learned to navigate by terrain features visible for seconds before passing overhead. Bomb aimers practiced the rapid target identification required when approaching at 300 miles per hour at treetop height. The Air Ministry established specialized low-level training units. 1,654 Conversion Unit at Wigsley focused exclusively on low-altitude tactics. Crews flew practice missions at night, maintaining 150 feet altitude for hours, navigating by dead reckoning and pilotage. Accident rates during training were horrific. Approximately 1 crew in 10 crashed during low-level training, killed by momentary inattention or navigation errors that resulted in flying into high ground. Flight Lieutenant Les Munro, who would fly in Operation Chastise, described the training. "We flew practice runs across the wash at night, maintaining exact height above the water while navigating to dummy targets. You had to trust your instruments absolutely while simultaneously keeping visual reference to terrain and other aircraft. It was exhausting mentally and physically. After a 4-hour low-level training flight, you could barely move your arms. The concentration required was unlike anything in normal bomber operations." By early 1943, Bomber Command had developed doctrine for low-altitude operations. Such missions were reserved for specific targets where surprise was essential and where no alternative approach existed. Crews required at least 3 months specialized training. Routes were planned to avoid known radar stations and fighter bases. Timing exploited darkness and weather. Weapons were specialized for low-altitude release. The human cost of developing these tactics was measured in crashed aircraft and dead crews. Training accidents killed more men than combat during the low-altitude program's early months. But gradually, crews learned to operate in the narrow margin between radar invisibility and ground impact. They learned to trust their instruments in conditions where visual reference was inadequate. They learned that survival at 100 feet altitude required perfection. Almost perfect was not good enough. The stage was set for Operation Chastise. The tactics existed. The training program was established. The crews were ready. All that remained was finding a target important enough to justify sending men into the radar shadow, and a weapon precise enough to be delivered at the suicidal altitudes that invisibility required. Barnes-Wallis would provide the weapon. Guy Gibson would lead the men. And the dams of the Ruhr Valley would test whether everything learned through blood and failure could be applied to achieve what no bomber formation had done before: arrive completely undetected over a heavily defended target in the heart of Germany. 21:39 hours. May 16th, 1943. Wing Commander Guy Gibson's Lancaster AJG lifted off from RAF Scampton's runway, its Merlin engines straining under the weight of the 9,000-pound cylindrical bomb slung beneath the fuselage. At 1-minute intervals, the remaining 18 Lancasters followed, their navigation lights extinguished, climbing into the darkness over Lincolnshire. The force divided into 3 waves. Gibson would lead 9 aircraft of the first wave directly to the Möhne Dam. 5 aircraft in the second wave would proceed to the Eder Dam. 5 reserve aircraft in the third wave would orbit over the North Sea, awaiting orders to attack backup targets if the primary dams were already breached. The entire operation depended on arriving undetected. If German fighters intercepted them during the approach, the heavily loaded Lancasters, flying at low altitude with limited maneuverability, would be massacred. By 2200 hours, the formations had crossed the English coast and descended to wave-top height over the North Sea. Flight Lieutenant Dave Shannon, flying AJL in the first wave, maintained exactly 100 feet altitude by watching his radio altimeter and the shape of waves below. The moon was nearly full, providing excellent visibility across the water, Shannon recorded in his diary. We could see the other aircraft in formation, black shapes against the silver sea. Every man knew that if we climbed higher, German radar would see us. Stay low, stay alive. The Lancasters crossed the Dutch coast at Vlieland at precisely 2300 hours, still at 100 feet. German radar operators at nearby Freya stations saw nothing. The bombers were below the radar horizon, invisible to detection systems designed to track formations at 10,000 feet or higher. As the aircraft roared across the Zuider Zee, Dutch civilians who glimpsed them couldn't believe what they were seeing. 4-engine bombers flying lower than windmills, their propellers creating visible wakes in the water. Navigation at 100 feet in darkness required absolute precision. Flight Lieutenant Henry Maudslay's navigator, Flying Officer Robert Urquhart, marked checkpoints on his map with split-second timing, a railway line, a distinctive bend in a river, a small village with a church tower. Miss one checkpoint and the entire formation could be lost. Hit obstacles marked on intelligence photographs. Fly into high ground. The margin for error was measured in seconds and feet. At 00:15 hours, May 17th, Gibson's formation crossed into Germany. They had flown 230 miles below radar detection. German night fighter controllers had no indication that 19 heavy bombers were penetrating deep into the Reich. Local flak batteries along the route had no warning. Several Lancasters passed so low over German barracks that crews saw soldiers standing outside, frozen in disbelief. At 00:28 hours, the first wave reached the Möhne Dam. Gibson climbed to 60 feet, activated the spotlights, and began his attack run. In the nose, flight engineer John Pulford watched the two pools of light converge on the water surface. Down a bit. Steady. Up slightly. And steady at 60 feet. Bomb aimer pilot officer Frederick Spafford sighted through his bomb sight, watching the dam wall grow larger. 425 yards from the wall, he pressed the release button. The 9,000-pound bomb dropped away, its backward spin at 500 revolutions per minute already imparted by a hydraulic motor. The cylinder struck the water, bounced again, struck the dam wall, sank to 30 feet depth, and detonated with 6,600 pounds of Torpex explosive. A massive column of water erupted 200 feet into the air. The dam shook but held. Flight Lieutenant John Hopgood attacked second. German flak batteries were now fully alert. Tracers arced toward AJM from positions on both sides of the reservoir. Hopgood maintained course through the storm of fire. At release point, his bomb dropped perfectly, but his aircraft was already on fire. AJM climbed away trailing flames, crashed 2 miles from the dam, and exploded. Only 2 crew members survived. Flight Lieutenant Harold Martin attacked third, his bomb striking the dam precisely. Another massive explosion. Still the dam held. Squadron leader Henry Maudslay attacked fourth. His bomb struck the dam's parapet, detonating early. The blast crippled AJZ. Maudslay nursed his burning Lancaster away from the target but crashed minutes later. No survivors. Flight Lieutenant David Maltby attacked fifth at 00:49 hours. His bomb was perfect. The explosion joined with the accumulated damage from previous attacks. The dam wall cracked. Water began pouring through. Within seconds, the crack widened. Millions of tons of water surged through the breach, creating a wave 70 feet high that roared down the Ruhr Valley, sweeping away everything in its path. Gibson's force turned toward the Eder Dam, arriving at 01:35 hours. The Eder was undefended by flak but presented a more difficult target. The approach required diving into a narrow valley, leveling at exactly 60 feet above the reservoir, releasing the bomb, then climbing steeply to clear a hill beyond the dam. Flight Lieutenant Dave Shannon made 3 attempts before aborting due to incorrect alignment. Flight Lieutenant Leigh Munro made 2 attempts before mechanical problems forced him to abort. Flight Lieutenant Dave Shannon finally achieved correct positioning on his 4th run at 01:52 hours. His bomb struck perfectly. The dam shook but held. Squadron leader Henry Maudslay's deputy, Flight Lieutenant Maltby, was already shot down. Flight Lieutenant Dave Shannon attacked again. This time the combined damage was sufficient. The Eder Dam breached at 01:54 hours. Another massive wall of water swept downstream. The cost was appalling. 8 of the 19 Lancasters were shot down. 53 crew members were killed, 3 captured. But the strategic objective was achieved. The Möhne and Eder dams were breached. Over 330 million cubic meters of water flooded the Ruhr Valley. Factories, power stations, mines, and transportation infrastructure were destroyed or damaged. German repair crews would require months to restore full production. The critical factor was surprise. Despite the presence of German radar stations throughout the approach route, despite night fighter bases in Holland and Germany, despite extensive flak defences around the dams themselves, the Lancaster force achieved complete tactical surprise. They appeared over the Möhne Dam without warning. German defenders had perhaps 2 minutes from first visual sighting to the opening of the attack. Those 2 minutes were insufficient to alert night fighters, vector them to the target, or prepare comprehensive defensive fire. Wireless operator Flying Officer George Chalmers, one of the survivors, wrote to his mother on May 18th, "We did what we trained for. The flying below radar worked exactly as planned. The Germans never saw us coming until we were right on top of them. If they'd had 30 minutes warning, if their radar had tracked us across Holland, the fighters would have been waiting. We'd all be dead. Flying at 60 feet saved our lives, even as it made the mission possible." 7,000 miles from the Ruhr Valley, American bomber crews in the Southwest Pacific were discovering the same fundamental truth about radar evasion. But where the RAF used low-altitude tactics for specialized missions against heavily defended targets, American crews in the Pacific would make masthead height bombing their standard operating procedure against Japanese shipping. The transformation began in late 1942, when Major Paul "Pappy" Gunn, a former naval aviator turned Army Air Forces maintenance officer, started modifying B-25 Mitchell medium bombers at his workshop in Townsville, Australia. Gunn removed the glazed bombardier's nose and replaced it with solid metal packed with 8 50 caliber machine guns pointing forward. He added 2 more 50 caliber guns in blisters on each side of the forward fuselage. The result was a flying gun platform carrying 12 forward-firing heavy machine guns. Gunn's aircraft modifications were purely tactical. Medium-altitude bombing against ships proved ineffective. Bombs rarely hit or sank moving targets. His solution, skip bombing, required flying at wave-top height, strafing decks to suppress gunners, then releasing delayed fuse bombs that skipped across the water, struck hulls at the waterline, and exploded below decks. Japanese radar in early 1943 was primitive. Most ships lacked detection equipment, and even the Type 21 radar couldn't see below 500 feet. American crews exploited this by approaching at 50 feet, invisible until within visual range. The tactic's decisive test came at the Battle of the Bismarck Sea, March 1943. Allied B-17 seconds first attacked from altitude with poor results. Then B-25 seconds and A-20 seconds attacked at masthead height, devastating the Japanese convoy. 8 transports and 4 destroyers sunk, over 6,000 troops lost, at a cost of 5 Allied aircraft. Statistical analysis confirmed skip bombing's superiority. Hit rates exceeded 30% versus 2% from 6,000 feet. Low-altitude speed and suppressive fire minimized losses. Heavy flak couldn't depress low enough, and light guns were silenced by strafing. By mid-1943, all Southwest Pacific B-25 seconds had solid gun noses and trained for coordinated low-level attacks. Despite the hazards, collisions, water impacts, and close-range fire loss rates averaged only 3 to 5%, far below medium-altitude missions. By war's end, skip bombing destroyed over 200 Japanese vessels. It proved that flying below radar, though perilous, delivered unmatched accuracy and surprise. Like British low-level tactics in Europe, it confirmed a universal wartime lesson. Altitude traded for invisibility could turn desperation into dominance. On May 17, 1943, German defences reeled as British bombers breached the Möhne and Eder dams undetected. Flying below radar range, they exploited physics no system could defeat. Despite new low-altitude radars, flak, and observer networks, low-level attacks stayed effective. Radar invisibility remained an enduring tactical advantage until war's end. Between 1941 and 1945, radar forced new tactics that redefined air warfare. Low-altitude flight, born of desperation, proved both effective and enduring. It offered accuracy, surprise, and survivability, unmatched at higher altitudes. Despite heavy losses and psychological strain, these missions shaped post-war aircraft, missiles, and doctrines built around radar flaw exploitation. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.